Zachary, oh, Zucker's on. Zachary, can you hear us?
Yes, I can hear you. Can you hear me there?
Yes. Yes. Okay. The next talk is from Tucker Jones from UCD, talking about Liger, next generation adaptive optics science with Keck. Take it over.
Wonderful. Well, thank you very much. I'd like to extend another round of thanks to the organizers for this wonderful meeting and allowing it to be hybrid. And I'm sorry I can't be there today, but it was wonderful to be there yesterday. And so I'm going to be presenting this on behalf of the entire Liger science and technical teams, a lot of excellent people. And I also just want to say, please do feel free to reach out on Slack or on email, in addition to questions at the end and so forth. So we'll get into it. Today, I'm going to tell you a bit about Liger, describe its capabilities, what it is, a brief overview of some of the science drivers, and really get across how it can benefit potentially your future science, your Keck science. And I'll give a short summary of the current status and activity that we're working on. So I'll start with what is Liger, or what is a Liger? So a Liger is the largest cat in the world. It's a real animal. It's a hybrid animal between a male lion and a female tiger. If you go the other way around, it's called a tigon. That's also a real thing, and it's slightly smaller. So here's a picture of Hercules, a Liger, and these guys can grow up to about 1,000 pounds. Liger, the instrument, is named after the cat, and it is a hybrid design based on the iris spectrograph for TMT, hybrid with Keck instrumentation. So it's not an acronym. It's a proper name, and it's named after the hybrid design heritage. And so the instrument itself is a next generation adaptive optics integral field spectrograph plus imager for Keck Observatory. And here we have a rendering of the instrument with the door wall cut away so you can see inside and see all the components in there. Just briefly to highlight some of the key team members, Shelley Wright is our fearless leader. I'm the project scientist. James Larkin is instrument scientist. Mike and Mark, I believe, are down there. And there's a whole slew of excellent people working on this to make it happen. So let's have just a quick look inside. What is this instrument? What does it do? Here is a schematic of the optical path. I'm not going to go through it all, just note the important parts. It's operates in the near infrared all the way from about 0.8 to 2.45 microns through the K-band with an imager and 2 integral field spectrographs. And in sort of the top middle, we have the schematic of the fields of view. And the 2 different spectrographs, a lenslet and a slicer, offer a selectable range of sampling and fields of view. So you can balance that for your science needs. And the spectrographs have a range of, they cover the full wavelengths at variable resolution. So you can select between 4,000, 8,000, and 10,000 spectral resolution with different band passes trading off the field of view. Good way to think about this instrument. Keck's current capability in this field is the OSIRIS instrument, and Liger is a similar concept, imager and integral field unit spectrograph, but basically better in every way. And the IFS itself, the spectroscopy, is essentially the design of the iris instrument on TMT, if you're familiar with that one. So a little bit, just to show you here, these are some renderings of the components that go into the instrument. And this is really just to illustrate that the design is really quite mature. It's ready to go. So here up on the top, we have some of the imager components, the detector and housing. Down below, some of the spectrograph components. Here's the grating turret, for example. And so this is the result of a lot of work over many years to bring this instrument into a fully mature design stage. All right, so let's get into Why build Liger? What's the motivation? Well, of course, principally, it's the science that it enables. And Liger specifically has a whole set of unique new capabilities that it would bring to Keck, enabling broad new science goals and investigations. So I'll just go through briefly on the left. Compared to our current capability with OSIRIS or with other telescopes and instrumentation that's out there now, Liger extends out to broader wavelength ranges, in particular pushing down to shorter wavelengths than our current adaptive optics instruments. A larger field of view, so about 4 times the field of OSIRIS spectroscopy at the same plate scale. And a big one is the higher spectral resolution. So with OSIRIS, we have a R of around 4,000 bit less, and Liger can push up to R of 10,000, which opens up a whole lot of new investigations. It's also more sensitive, and you can have a parallel imaging mode. That's the default, to run the imager at the same time as the spectrograph. So there is a lot of science that drives this design and that you can do with this design. Down at the bottom, I have highlighted some of the key science drivers that are really fully fleshed out. But off to the right on this table is just a whole long list of some of the example cases that benefit or that really require these capabilities. But the big picture for why Liger really is, well, the Keck science community. It's you, all of you in the room and out on Zoom. And the takeaway here is Liger is a broad workhorse facility instrument to do a lot of frontier science, ranging from the solar system out to the most distant galaxies with Keck. So what I'll do now is just give a couple of the examples picked out from some of these key science drivers, which, again, to emphasize, really drive the design of Liger and how it really pushes science forward. So great example is the Galactic Center, and we heard a really nice talk on the Galactic Center earlier today from Abimat. And Liger really can push on the testing of fundamental physics around the supermassive black hole in the Galactic Center in multiple ways. So one, which I won't actually talk about, but is, do the constants of nature vary in a strong gravitational field? Does the fine structure constant change when you're close to a black hole? You can ask Tuan Do all about that one. I think he's there in Pasadena. Is general relativity correct? How do supermassive black holes affect their host galaxies and environments? Well, on the left, we have this lovely image that we've seen of the stars orbiting around the supermassive black hole in the center. And that's come from many years of exciting adaptive optics imaging, and bringing in the spectroscopy. It really allows a lot of very exciting new science. And here is that this is the Galactic Center zoomed in to the central few arc seconds. And what I'm showing here is the OSIRIS field of view and the Liger field of view for integral field spectroscopy. So you can do wholesale spectroscopy with more sensitivity and higher spectral resolution, which is key for some of the new physics, the new science that we can't do today. And just some of the parts, even just related to the orbits of stars, are to be able to orbitally map with spectroscopy multiple short period stars, test relativity through their precession, and look at the extended mass profile. Is there actually a cusp of old stellar remnants in the center of the galaxy or not? And so having the sensitivity, resolution, and field of view really pushes this forward in a way that's either extremely challenging or downright impossible today. So going on to another case, one that I find fascinating, they all are, is dark matter and dark energy. What are they? What's their nature? Liger is designed to be ideal for studying, for making cosmological measurements, for example, with gravitationally lensed quasars. And here's just a schematic of what's going on. You have a distant quasar located behind a massive galaxy, which acts as a lens. And so that quasar becomes strongly lensed into multiple images on its way to our view at Earth. Actually, forget Hubble, we're going down to the ground on Mauna Kea at Keck. And by looking at the ratios of the fluxes of each image and the difference in arrival time from variability in the quasar, you can study a substructure of dark matter and measure the expansion rate of the universe and try to understand what dark energy is. So that's the schematic on the right is a simulated image of a real system from Liger. This is what we expect to see in about an hour and a half of integration. Of course, with Liger, what you want to do is go and get the spectra as well. Here's the same system, and this is the faintest image of the quasar, and the green is the expected performance with Liger in an hour and a half. Now, this is to study dark matter, and the key is to look at these narrow emission lines. So we're showing the sulfur 2 doublet here in that little green box. And compared to what we can get with OSIRIS right now, we really get quite a large gain from Liger, plus being able to map the whole system at once. So it's nonlinear gains. And in fact, what this gives you is about a 10 times improved constraint on the dark matter half mode mass, which pushes you into the regime where a dark matter halo does not host a galaxy. So this gets you into the darkness, the true dark matter, where you don't see any luminous tracer, which is where you want to be to go and test, is dark matter a cold particle? Is it warm? Is it fuzzy? Is it something else? One more quickly that's more in my wheelhouse that I'm quite interested in is looking at the evolution of galaxies at high redshifts. And so here on the left are some nice recent images from the James Webb Space Telescope. And these are high redshift galaxies, and they're not the sort of thin spiral disk galaxies that we see today exactly. So Liger is going to be great for mapping out how galaxies form, how thin disks emerge. And one of the key things we really need to get that understanding of how and when the thin disks form is higher spectral resolution. So Liger is an instrument that can deliver this, plus get all the key emission lines that we want simultaneously to map the metallicity, which tells us about the feeding and feedback in these galaxies. So this is a really key thing. Even James Webb cannot do this sort of science because its spectrographs don't reach the spectral resolution that we need. So one other quick comment on this, one of the things that we'll be doing with Keck Observatory as a community in the next several years is a whole lot of key science with Kappa. One of those programs is the formation of high redshift galaxies, and we're planning to throw 20 nights at it to do a big galaxy survey. This is something that would have enormous gains with Liger because you don't need multiple tunings. You get excellent sensitivity and resolution. You get the higher spectral resolution that gives you science that just can't be done even if you wanted to spend a whole lot of time on a single object. And so that's what Liger really opens up. All right, so very whirlwind tour, and just again to emphasize, there's a whole range of science drivers that we've considered in the design of this instrument. And this is just a snapshot, a small amount. So let me give an update on the timeline and activities. Liger currently is in the final design phase with a final design review coming up this December. It's ready to go. And this really draws on many years of heritage design, both from TMT and IRIS and dedicated Liger design for Keck. So we're ready for fabrication early 2023. We're funded through FY23 currently. We'll be seeking additional funding. We've been encouraged from NSF to submit there as well to continue. And our target is to be on Sky in 2027. So I really hope that in 5 years or so, I can be here at the Keck Science meeting telling you about new science with Liger. Meanwhile, there's a lot of activity on both the science and technical side. For the science team, setting the requirements, use cases, we'll be participating in verification. Just a brief shout out here, we have 33 members currently on the science team spanning 18 institutions. It's very broad, that's the whole point. And our mission is to make Liger be able to do the most impactful science. We welcome participation, so please, if you're interested in joining and contributing, get in touch. You can email me or reach out on Slack or whichever you prefer. And with that, I'll just leave you with the summary. So the main takeaway that I hope you get is Liger is really designed as a powerful, versatile, adaptive optics instrument to do a broad range of science. And please do consider it for your own science. And it's the instrument that we want to keep Keck adaptive optics science truly at the forefront. And I can take some questions. Thank you.
One very quick question. Have a question. Everyone is intimidated by. Yes.
Is there a single headline number I should think of for like relative surface brightness sensitivity compared to Osiris?
I'd say not exactly a single one because there's so many different modes beyond what Osiris can do. But I could give you a if you want a 1-to-1 with Osiris, you know, matched resolution and something, it's about 2.5 times the sensitivity of what we have today.
We have to move on quickly. Thank you very much.